Hello everyone, this is the video lecture for Calculus 3, section 16.6, parametric surfaces. So I want to give you two, conditions before we jump in here. This is all about patterns and graphs, and we'll see a couple new formulas here and there, but we'll definitely be seeing patterns, and I'm going to show you those patterns. The other thing is that I can't really draw so perfectly for you here. I'll try my best, but obviously a computer will graph something in 3 dimensions better than what I can do. So I'll do my best. Here we go. 166003. So they start us with an R in terms of UV, which is equal to, I got U plus VI plus 3 minus VJ plus 1 plus 3U plus 5VK. That's a 3 right there. Okay. And so they're wondering what kind of graph is this? And it's essentially a multiple choice. I'll tell you it's very simple here. This is actually a plane. But let me tell you why. The reason why is because there's only linear terms. So only linear terms. That really helps. I mean, honestly, that's about it. So I don't have a lot of other things to say about that. You only got linear terms, it's got to be a plane. Next question. Keep moving. 166005. I've got R in terms of ST, which is kind of unusual. Normally they just do U's and V's. But we got S times cosine of T, S times sine of T, and then an S. Okay, so let's talk about some patterns. This right here is circular. Okay, it's circular. But notice that my radius is variable. My radius is variable. Okay, so it's kind of interesting. I got a circle on my XY plane, and yet my radius is variable. That's why I'm going to say it's not a circle, it's circular. Okay? It's just going to go around and around and around, but it might come small or big or whatever if you can kind of see my cursor. But then notice that Z is equal to the radius. Okay? Basically that radius that we had, Z is equal to the radius. That's my height. My height is equal to the radius. And so what's going on here, if you know Z equal to the radius, basically that's going to be a cone. It's a cone. Okay? Oops, let me draw that a tiny bit better there. Woo. There you go. And so it's following a 45-degree line. I probably didn't draw a 45-degree line very well, but because my variable radius is equal to my height, I'm going to have a cone. So cone is the answer. Notice that again we have circles, but their radius varies. Circular. Okay. 166013. So now I got little r's equal to U cosine V, U sine V, V. Now notice this time it's a little different. We got circular, just like last time, but notice that V, my Z is equal to V, which is kind of like my theta, my angle. So I'm saying that my Z, my height, is equal to the angle in which it is. So, but I still have this variable radius thing. I am not going to be able to draw this the best, but I will try my hardest here. Let's assume a fixed radius for just a minute. We got a circle, and then everywhere my angle is, it's also the height. So the more angle I get, the higher it goes. And so essentially it's going to be a spiral going up. Now notice that this is cool and all, but I said beforehand, hey, let's just assume a fixed radius. What's going on is that it could be any kind of radius. So let me just kind of make an example here. So we got a spiral here, and then we got the same spiral here. Okay? And if you can barely tell, it's actually, if you go up and up and up, it's actually a staircase. Can you see the spiral staircase? It's like a spiral staircase going up, 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 up. And so this is down to the ground, spiral staircase. I'm going to write that down. Spiral staircase. I know that's like not a technical math answer, but you'll definitely be able to pick out which answer it is from that. 166,016. This one's a little different. I got x is equal to 1 minus u times 3 plus cosine v, and then times cosine of 4 pi u close close. Y equals 1 minus u, 3 plus cosine v, and then I've got now a sine of 4 pi u. My z is equal to 3u plus 1 minus u sine of v. This is one huge mess. Perhaps you could see this as multiple choice, and it's not a plane, it's not a cone, so you can maybe, like by process of elimination, get rid of some stuff. And so really, I'm going to tell you that it looks kind of like, to me, like zooming out, it kind of looks like spherical coordinates. Spherical coordinates. Just a little bit. Notice that we have, these guys have the cosines, but then here we got the cosine sine, and here, opposite of the cosines is a sine. This is kind of inverted from spherical coordinates, but it's kind of similar in a way in design. So spherical coordinates means like spheres or like balls. Okay, for just a second here. Notice that right here, this guy, the z is going up, but it's going up according to its radius. See the radius right there? So my radius and my height are connected. They're not perfect, but they're connected somehow. So radius is somehow related to the height, your z. Okay, so we got a ball or a sphere, and its radius is kind of connected to height. I'm going to tell you, it really is a process of elimination at the end. I'll draw it the best I can, but essentially, it's a horn. It's a horn. Let me try my hardest here. Okay. So it looks like a big old tuba thing. It's a horn. And I'll describe why that the horn makes sense here in this case. So I'm not the best horn drawer in the world, but, well, there you go. There's your horn. It looks kind of like a horn that kind of goes down, 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 and then, out comes the music. If you put your mouth right there and you're singing into it, kind of thing, or whatever you're doing to it. Regardless, though, how do I know this? Well, look here. I got spherical spheres, balls, and its radius dependent on height. You're not seeing it, but actually, it's not just circles, but like you can fit a ball inside of that essentially. It kind of think like gumballs that can like roll down, 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 something like that. But the radius of that sphere is increasing as you're going down. Just a thought there. Okay, moving on. So the next questions are more analytical, and so let's do that. So I got 166,019. They say to find the parametric surface. Parametric surface. Now there's many answers for this. I'm going to just choose one that works for me. They might have an entirely different answer. It kind of depends, but we get to pick a little bit. We have a little bit of freedom here. They want it for a plane that's through the origin, and it contains the vectors 1, -1, 0, 0, 1, -1. Okay. So I don't know exactly what this looks like, but we have a plane. Like a plane, basically, it's like a sheet of paper, and they're saying we're definitely at the origin, and we have these two vectors somehow in the plane. And you can see how we can create a plane from a point and two vectors, essentially just kind of connecting those. You got a triangle extended out forever. There's your plane. How we define plane equations is going to be through its normal vector, okay? That's kind of like, you can say it's like it slopes, the slope of it. And so that's what I'm looking for. I want to find the slope of this plane. So how do you do it? It's with the cross product. So I'm going to cross product 1, negative 1, 0 with 0, 1, negative 1. Always start with a 0, 1, K, negative 1. Two negatives make a positive, actually, J. A 0, always a 0. Two negatives make a positive, I. 0, 0, 0. And so what we end up with is 1, 1, 1 is my normal vector, or you can say, again, it's kind of like your slopes. And so in the end, you actually can have a plane here. It's a very simple plane. 1, x minus 0 plus 1, y minus 0 plus 1, z minus 0 is equal to 0. This is from way back in the day. A x minus x naught, da da da. Well, I was essentially using the point 0, 0, 0 because they said it was through the origin. And so my, I guess, plane equation is this guy right here. Okay, but here's the problem. They don't want the plane equation. In the end, they want the set of parametric equations to make that plane up. And so what we have to do here is we need them in terms of u's and v's. So we need, like, I guess, r in terms of u and v. It's kind of like what their answer is supposed to be. How do we do that? Well, I have to just pick something out at some point. Let's just say, let's say that we have, and I'm just making this up, x equals u and y equals v. I'm just making it up. If that's the case, then what I have is u plus v plus z equals 0. Move this over, and so z is equal to negative u minus v. So I have these guys and this one here. That's literally my answers. That's what I'm going to type in. And this is where it gets a little, just a tiny bit aggravating. This is what I thought would be the answer in WebAssign, but that's not how they're wanting it. You need to type x equals u, comma, y equals v, comma, z equals a negative u minus v. So this is what they want you to type into WebAssign. Okay. Let's do this again. 16.6.021. So it says we have part of a hyperboloid, and then they got 6x squared minus 6y squared minus z squared is equal to 6, and it says that lies in front of the yz plane. So in front of it. What does that look like? Well, the yz plane is this guy here. So this is my yz plane, essentially, and I'm in front of it, which I'm assuming is going to be positive. Notice that this is a hyperboloid of 2 sheets. And going way back, it's because I have 2 negatives. So then x is kind of like your odd man out. If you remember, this is long ago, the odd man out. So hyperboloid of 2 sheets generally has like 2 different cups, essentially. And so the odd man out is the one where its axis is there. For that picture, it'd be z. Here we got an x. So essentially I have this hyperboloid. It's a hyperbola. Lloyd. And we have another one over here, but they don't really care about that one. So they only wanted this guy, again, in front of the xy plane. If you're wondering, that plane extends out everywhere, so you don't really have to wonder, like, oh, it's only going to, octant 1. It's not like that. It's just this whole entire cup thing, okay? So they want this cup thing to be in parametric form. All right, so how do we do this? Well, first off, if I get like an x equals, I'm sure I can probably get something to work. So let's start with that. I'm going to take this here and start working on it. Let's first off move these variables over here. So 6x squared is equal to 6 plus 6y squared plus z squared. Divide by 6. X squared is equal to 1 plus y squared plus 1/6 z squared. Square root, And you would think, oh, but you need a plus and minus. Actually, that's incorrect in this particular problem. Reason why is because we have a positive end. Look, this is a positive side of it. There's that negative one over here that we didn't need. We're only looking at the positive. Therefore, we don't need this. We would simply just say positive, and that's our answer for x, okay? With this, I'm going to say, let's just say that y equals u and z equals v. And if that's the case, then I got x is equal to the square root of 1 plus u squared plus 1/6 v squared. And like literally, that's your answer. There's your answers combined. You put them all in one box, obviously with commas, but there's your answers. You see how I'm just creating my y and z just out of thin air, but I'm trying to make it easy. I don't want to make it complicated. And WebAssign should be taking these. They should have some freedom there. Again, if they're not, you just tell me and we'll talk about it. X squared, y squared, z squared is equal to 36. And it says that we want to be above the cone, and they give me a cone, z equals square root of x squared plus y squared. Notice that it's only positive. Also notice that's my radius. So z equals r. It's my cone. We already talked about one of those earlier. Z is greater than this much right here. Okay. So what that's telling me is that it's the positive only. I just see positive all over the place, so positive only. Like normally when we say cone, and we draw a cone, technically the cone is on both sides. But I'm thinking that they're only wanting the positive end of this here. And so I'm just going to assume here that x is equal to u and y is equal to v. And if that's the case, then, well, z is equal to the square root of u squared plus v squared. Actually, this is... Hold on. This is actually a little incorrect. Hold on. Because I know that it's on the cone there, but it says we're above the cone here. And so I wonder, perhaps, we're talking about this circle action up here. I'm not entirely sure, but they say above the cone. So this is not exactly right. That would be too easy, I think. Did we ever use our... Oh, it's a sphere above the cone. Silly me. Sorry. Okay, I should have... Look, I even wrote it down. It's a sphere above the cone. So it's like an ice cream cone. Think we got the ice cream ball, and then we got a cone that it's being held in, right? Well, what's happening is that ball, that sphere, is merging perfectly with the cone at some point. It's like the widest part of that circle is right here, and then it would keep going, and probably it has to mush into it, of course. It would extend past if you really wanted to know. But that's my sphere here. It's my ice cream cone, essentially. I want to know what the surface area of that sphere is above the cone. So that's why I'm saying positive only. Okay, sorry. I was a little confused. I forgot about the sphere part. So, in order to find the sphere, we're not using this guy. We're using this guy to find our z. Obviously, just move this stuff over and square root it, make it positive. As we've already said, there was only positives we should care about anyways. So it's 36 minus x squared minus... whoa. What's x and y equal to? U and v. There you go. Okay. I just moved it over and square rooted it. Sorry for that confusion. That's why you should watch to the end. 16,6,033. So I've got x equals u plus v. I've got y is equal to 6u squared. I got z is equal to u minus v. And they give me a point 2, 6, 0. And they say find the equation of the tangent plane at point P. I have no clue exactly what this is going to look like, but let's just say I've got some kind of surface. That's definitely not what it looks like. Something like that, kind of like a waving flag or something. Cool, that's good enough. Okay, so like let's just say I have a point P right here, and so I want the tangent plane for that. And so it's going to definitely not be perfect, but it's going to approximate anything around it, etc. Well, if you notice it's a plane, how do you make this thing work is with your normal vector, right? Your little normal vector is going to be your slopes. That's at least something in my horizon for how we're going to see this, but let's just go through some process here and see if I can get like some kind of an equation going on. So with all these, can I get rid of the parameters? Well, let's start with my y's, actually. So y is equal to 6u squared. Can I solve for y, let's say? So I got y divided by 6 is equal to u squared, and u is equal to plus or minus the square root of y over 6. Okay. What if I started solving for these guys? So then I have a u. What if I had x is equal to my u and v? So my u, then plus v, and my z over here is that same thing, plus or minus square root y over 6, then minus v. So if I could take maybe this equation for a moment, I'm going to solve for v. So in order to do that, I'm going to move it over, move this guy over. So v is equal to plus or minus the square root of y minus over 6, y over 6. Minus z. This I can plug in here. So now I got plus or minus the square root of y over 6, and then plus, and then I got plus or minus the square root of y over 6 minus z. Wow. Well, here's the thing. And it's important to note that this plus minus that you have here is the same as this plus minus here. We never moved this to the other side. We never changed it. Like, honestly, if I were to move this over, I'd have to say minus plus, and that's different than plus minus. So we have to watch out that this is in fact a plus minus, and that's a plus minus. They're actually the same. And so you can combine them to say 2 of these square roots. And then, of course, this plus sign distributes, I guess, to this negative z. Okay, so now we have right here some type of an equation thing that is not perfect, but it has all of my x, y's, and z's put together. Let me move my z over. So x plus z is equal to plus or minus the 2 square root. I'm going to divide by the 2. So x over 2 plus z over 2, whatever you want to do there, is equal to plus or minus the square root. I'm going to square both sides. You know what? I kind of like it all divided by 2. That way I could just say that's all divided by 4, right? So I'm just doing that instead. So x squared, x plus z squared. I think that I like that better. And then just y over 6. We're really close to the end. Let's see here. Let's move this 6 over. So then I've got 6 over 4. And I'm going to go ahead and FOIL this thing out. X squared plus 2xz plus z squared is equal to y. This is technically 3 over 2. But what I want to do is, I think I want to distribute it. Yeah, let's go ahead and distribute this everywhere. And so I got 3 over 2x squared. The 2's here are going to cancel and make a 3xz. And then I've got 3 halves z squared. Let's move this y over, so minus a y equals 0. And what we have here now, finally, is I have a cap f. I have a function that works for this surface, a function for this surface. And when I set it equal to 0, what I can now do is I can now find f sub x, f sub y, and f sub z, which are essentially my slopes. In a way, they're creating my normal vector. Oh, in a way. So let's go and find my partial derivatives of each one of these. So the 2's come down, so I got a 3x. For my y, basically just a negative 1. Whoa, I messed up on my x. Sorry, I did my x fine there. But what about this guy? Is 3z. Okay, now we're talking. A negative 1 for that. For my z, I got a 3x, and again, the 2 comes down, cancels, and a 3z. Cool. And so then I want to find out, I guess, this normal vector at point P. And so then I'm plugging in my point P. If you remember, that was a 260 for my x, y, and z. And I can plug that into each one of these. And so then my slopes are, let's do fx at P. 3, and then I'm going to add up my z and x together to make a 2, so I got a 6. F sub y at P, it's just -1, and f sub z at P is equal to basically the same thing as 6. Okay. Cool. So then I can take those as my slopes on my big equation here. So 6, x minus, and again the 2, minus 1, y minus the 6, and then I guess plus 6, z minus the 0 equals 0. You can see I have my point, and then I have my slopes. We're basically done. You could, distribute and make it look pretty. So 6x minus y plus 6z. When you distribute this one, and, well, that one's going to be a 0. This one here, I actually have here a -12, and on this side here we have a +6. And so this right here is a -6. I can move it over, and so that's my final answer. There we go. There's my tangent plane. There's a lot of math there. 166035. So again, they want the tangent plane. Tangent plane at a point. Okay. So they give me my, I guess, surface is u cosine v, u sine v, v, and we've seen that before. And they say they want it at u equals 7 and v equals pi over 3. So they want the tangent plane at that particular point. Another way to find that normal vector in these kind of cases is by using this kind of weird formula here. It's r sub u cross r sub v. And we're going to be using that in other questions, so I think it's probably a good thing to go ahead and get it started right now. So I'm going to find my partial derivatives in terms of u and v. So in terms of u, cosine v, sine v, and then a 0. And I'm going to cross it with my r sub v. So in terms of v, we got a negative sine. Oops. That's going to be a v. Sine goes to cosine. And then a 1. Okay, so now we got to do the cross product. Notice that I got this thing equals, and I put a cross there. I know it's bad notation, but it'll work. So always start with a 0. Cosine and cosine will make a u cosine squared vk, and then anything times 1 is itself, cosine v, and that would be a negative j position. And I put the negative on the front already. Here, again, that's a negative k. 2 negatives make a positive, so u, and then sine squared vk, always a 0 in the middle, and then times 1, this is a positive I position, so sine v I. 0 times anything is 0, so you can just get rid of all those now, finally. So my I got a sine v, my j, I got a negative cosine v, and my k, I got u times sine squared v plus cosine squared v, essentially. We'll notice that this guy right here equals 1. So you can just basically get rid of that one. Much easier to work with. And so they want it at point P. And the P here, I guess, is labeled as u's and v's. So 7 comma pi over 3. It's my u and v. And so I'm going to go and find out what that is now. So here we go. Plugging it in, sine of pi over 3, that's going to be 60 degrees, so square root 3 over 2. Cosine is going to be a half, so negative half. And then just u is just, well, it's a 7, so there you go. Kind of distinguish it with a little dash there. That's my n. Again, that's my normal vector. That's my slopes. And so with my slopes, I can just simply go real quick and, oh, I see. Okay. Sorry, I was looking at my paper for a second. I need then, these are my slopes, all right? So I got square root 3 over 2, x minus what? This is supposed to be x naught. What do I put there to make that work? What's my original point? Well, notice that we have a u and a v, but not original x, y, and z. So I'm kind of like wondering what goes in here as we keep going. Well, we take these and we plug them into the original. So just for a second, kind of ignore that for a second. Let's go back to the r original at 7 comma pi over 3. I'm going to say original. I mean, this is like the very first r that we were given right there, okay? So I'm basically taking these and plugging them in to the original. And so what do we get? I got 7 times a 1/2. I got 7 times a square root 3 over 2. And then I get the pi over 3. And so this here is my x naught, y naught, and then z naught, essentially. Or my x, y, and z. Now I can go back and do my slopes and my point. So here we go, finally. Square root 3 over 2, x minus 7/2. Be a minus there. Minus 1/2, y minus 7 square root 3 over 2. And then plus 7, you don't really have to do that, z minus the pi over 3, and then equals 0. And that should be good enough. Now, I'm going to just simplify it real fast to what they had, but this, I think that's going to be fine up there. Okay, so they got 7 pi over 3 in the end. I think some stuff canceled, essentially. Okay. Next question. So, they want 16,6,039. They say find the area of the plane, and then 5x plus 2y plus z is equal to 10 in the first octant. Now you can actually draw this plane out. This one's pretty easy. If you set z equal to 0 and y equal to 0, you get an x equal to, and you divide by the 5 is a 2. So you get a 2 there. Same thing here. If you set x and z equal to 0, divide by the 2, you get a 5. So y is 5. So 2 and 5. And then finally, if you set x and y equal to 0, you get z equals 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's 10 for z. Again, this is x, y, and z. And these are where they are touching those axes. Ooh, pretty close. There we go. So here's your plane. There you go. One thing to note before we keep going, what does it look like on the XY plane? Well, it looks like a triangle. Again, this is at 5 and this is at 2. I might have to use that later, so keep this in mind here as we keep going. So here's your formula for the surface area, okay? So surface area of any kind of, I guess, surface like that is double integral of the magnitude of, let me kind of redo this here, okay? I'm going to do doubles. Those singles are still fine. R sub u cross R sub v magnitude dA. Notice that this right here is essentially my normal vector yet again, right? But then I find its magnitude. So that's going to be like square root of who knows what. And then we finally have to integrate in terms of area. And that's what this dA is going to be. It's basically dy dx. So we're looking at the shadow in which it's cast, and then the normal vector of like a tangent plane essentially at any point. So let's find this out. So my r is, and what I have to do to make r is kind of funny. If you remember my plane equation, it's right here. What I'm going to do is move these over and z equals 10 minus whatever. I'm going to say that x is equal to u and y is equal to v. So that's my x and 1y. And my z, if you go back up, I move it all over. So then I got 10 minus 5 u minus 2 v. So that's my r vector. So now I got to find ru, and I'm going to cross it with rv. So 1, 0, negative 5. In terms of v, I got a 0, 1, -2. Always start with a 0, 1k. 2 negatives make a positive j. 0 times anything is 0, so that's all going to 0. 0, we got a -5, but that's a negative I, so a positive in the end. Positive 5i, and then a 0. So we got 5, 2, and 1. I need the magnitude of that. So that's going to be the square root of 5 squared plus 2 squared plus 1 squared. I want to say that it's actually lucky what we've gotten here. This is going to be square root 30, because this right here being numbers is not always given. It's cool that we got numbers this time. Sometimes we don't get numbers. I would say just watch out. You could get a whole mess of stuff, and then you have to integrate something else. So just watch out for it. So I got square root 30. So really what it comes down to is my surface area is double integral of square root of 30 dA. You know what's really funny is that going back, we already have the area of that triangle, right? What's the area of this triangle? It's 1/2 base times height. And so, just to be funny about it, you can do 1/2 base times height, and so you get 5 square root 30. And there's your answer. It's cool to do like cheater stuff like that, you know, where you don't have to actually do the integral. At least if it's something simple like that. Okay, again, find the surface area. And they say my surface is z equals x times y, and it's going to be inside of the cylinder. X squared plus y squared is equal to 64. Okay, so I need to find out my surface here, an r vector for it. So let's call it u, v, u times v. I know that's kind of cheating again, but hey, it's easy to do. Might as well. So r in terms of u is a 1, 0, v. R in terms of v is a 0, 1, u. Crossing them, 0, 1k, and then I got a negative uj. 0 times anything is 0. 0, I got a negative vi, and then a 0. So I got negative v, negative u, 1. Notice that we don't have just plain old numbers this time. So my magnitude is going to be negative v squared plus negative u all squared plus 1 squared. You see what happens here though? U squared plus v squared plus 1. This is kind of interesting. So what I want to do is I want to now do my area. Basically that's going to be my answer, is double integral of this guy here, dA. But now I need to find out what my area is supposed to look like and stuff. And what's this surface inside the cylinder? What does it look like? Well, it's this guy here is one of those saddles. It's a saddle essentially. So I've got some kind of saddle thing going on. Okay. Cool. I'm not really too concerned about the saddle, but what I'm really concerned about is the cylinder. Cylinder, it's inside the cylinder here. And my radius for that would be 8. So what I'm seeing is that when I'm looking at dA, I'm looking at this circle down here, a circle, and how do I find that best is probably with polar. And so I'm going to convert my dA into polar form. So I've got now essentially this guy right here. If you go back, I have my, right here, x and y. Right? X and y is u and v. And so I can replace these in a weird kind of way with saying x squared plus y squared plus, plus 1 dA, right? If I can convert that. And this actually ends up being my r squared. Okay, so that's kind of a little bit of a jump, but I'm going, converting this back over to something that was original, and now I say, oh, X, Y, and that's polar mode, and I can do that. r dr d theta, and I'm going from 0 to 8, 0 to 2 pi. Notice that we'll have a u substitution here, r squared plus 1, du is 2r dr. So essentially I'm going to divide by the half, 0 to 2 pi, 2/3 power, r squared plus 1 to the 3 halves, from 0 to 8, and then d theta. So the 8 and the 1 both get plugged in. You're going to get something from both of those guys. The 2's cancel. You get a 1/3 in the front now. And so 8 squared is 64. So basically I get 65 to the 3 halves. And then when I plug in a 0, I get a 1. So minus 1 d theta. Well, notice that we don't have any thetas. 2 pi slide. Just pop a 2 pi down there. And that is the answer. Cool. All right. This is the last problem. I'm going to tell you that I messed up on this problem quite a bit. Sometimes on my notes, most of the time on notes, I mess up somewhere, but I'm able to erase it and stuff. I messed up so badly on this, I had to actually scratch through a lot. I just didn't have the eraser for it. Find the area of the surface. So just like we were doing last time. I got x equals u squared, y is equal to uv, and z is equal to 1/2 v squared. And they're telling me ahead of time that u and v are between 0 and 3 and 0 and 1. Okay? Now, this is going to be the indicator to tell you how we're going to proceed in a couple minutes. But until then, let's kind of just solve for, let's kind of like make my r's and stuff like that. So my r vector is u squared, uv, 1/2 v squared, r sub u is 2u, v, and then a 0. And then in terms of v, I got a 0, u, the 2 comes down to make just a plain old v. Crossing them. Always start with a 0. I got 2u squared k. I have a negative 2uvj. 0, 0 in the middle. I got a positive v squared I. And then anything times 0, 0. So my i's I got v squared, my j's I got a negative 2uv, and then my k I got a u squared, 2u squared. Okay, awesome. So we need to find its magnitude. Obviously, that's going to be the next step for my integral. So when I'm squaring all this stuff, v squared squared, negative 2uv squared, 2u squared squared. Sorry. You get v to the 4u squared v squared, and there we got a 4u to the 4. Okay, there's not really a lot to change right now. This is exactly where I messed up. I started to say, well, let's convert it back to x's and y's, and then I could start finding my dA and all that stuff. Well, if you go back up, they gave you limits in terms of u's and v's. So what we have now is actually good enough. And so let's actually just go right into my integral. Let's do du dv of this big square root thing, v to the 4th, 4u squared v squared, 4u to the 4th du dv. This should do it. So now we, of course, have got to figure out how to do this. Looks crazy, right? But this should be the answer. This is definitely going to be my answer. So how do we go about accomplishing that? Well, notice that there's kind of a pattern on the inside here a little bit. And I don't know if I had to look it up or not. I can't remember, but you know, some of these are just difficult without some additional assistance. I went and saw, and I'm pretty sure I did that it was v squared plus 2 u squared squared. Okay, so essentially this is like a perfect square thing. That's why you got the 2 plus 2 makes a 4, but 2 times 2 makes a 4. See that? How that works. All right, and then the square and square root cancel. So now we're left with v squared plus 2u squared du dv, which is so much easier. Let's go ahead and do my first integral in terms of the u. uv squared plus 2/3 u cubed from 0 to 3 dv. Plugging in the 3, the 0 is going to cancel it. So I got a 3v squared plus, and notice that I got 3 cubed divided by 3. It's going to make 3 squared times the 2 is actually an 18 dv. So now I integrate in terms of v. When I do cubed over 3, it's going to cancel. 18v from 0 to 1. The 0 is going to cancel, obviously. Plug it all in, you get a 19. Okay, that's it. We're done. Thank you very much. Have a great day.